Hello beautiful people, my name's Brian Hubben and I'm making this video for my Intro to Statistics class, and the topic in particular is conditional probability in the context of continuous random variables or the normal curve. So this is a worksheet that we have for Module 8 and I'm actually looking at the solution key for 8.6 to 8.8. Suppose that some exam scores have a normal distribution with a mean of 80 and a standard deviation of 5.9. All right, so here's the curve that would relate to that. Of course, you'd have 80 in the middle, 5.9 gives us a sense of how wide it is, and some of the calculations below have us using this 12% value. Most of these calculations are pretty straightforward with the TI-84. You'll see the commands listed in the entries, but it's part G that tends to give people a harder time. If we go down to part G, move my head. Given that a student received an A, what is the probability that their score was above 90? Okay, so up above, it said that if the top 12% of students receive an A on this exam, what is the cutoff score for an A? And the cutoff score for an A would be 86.932. So given that a student received an A, which we can think of as given that the student received a score of greater than 86.932, what is the probability their score was greater than 90? So what's the probability of obtaining a score greater than 90 given that the student received a score greater than 86.932? All right, so from our earlier definition of conditional probability, when you have a conditional like this, you AND the two pieces. So you're going to have probability that a student got a score greater than 90 and the probability that the student got a score greater than 86.932 divided by whatever comes after the given bar. What comes after the given bar here is x greater than 86.932, so that goes in the denominator. And we actually know the answer to that from part F. We know that's going to be 12%. The part that's not always so obvious is what happens in the numerator here. Why is it that the probability of getting a value greater than 90 and greater than 86.932 is just the probability of getting a value greater than 90? So let's switch over and look at a graphic that will help us to see the logic behind this. All right, so here's that same curve, but a lot more attractive because it's in color on my iPad. So same curve, I still have 80 in the middle, and 86 is going to be closer to 80 than 90. So if I draw a line here, and let's say that's 86.932, and x greater than means that we would shade over to the right. So if I shade over to the right, that area that I've just shaded denotes the probability that I get a value greater than 86.932. Now I'm also interested in x greater than 90. So let's give that a new color because we can, and I paid a lot of money for this iPad. So if I go here to 90, and I get shady to the right of 90, it now becomes visually apparent that since when we have an AND statement, so if we go back a ways, we talked about the probability of getting a king and a heart, a king of hearts. So we had the Venn diagram of the circle with another circle, and then the overlap was king and heart, where one circle was king and one circle was hearts. Well, similar idea here. When we have this AND statement, we're looking for the overlap. And when you look at this, you can see that the green area is in common both to the right of 90 and to the right of 86.932. So that's going to be the overlap. So that's why what we have written up here is really equal to just the probability we get a value greater than 90. So again, that's explaining the logic right here. Why is this statement equal to this statement? And of course, we have a TI application that helps us figure that out on our TI-84 to get a value. There's another way we can look at this, though, that'll get us to the same result and tie into something that we saw earlier. So if we go back to some of what we saw back in Module 7 and also 6.3, we were talking about conditional probability. So we had a nice contingency table here that talked about male, female, and then different degree levels. So this would tell us that since, for instance, 27 males got doctorate degrees, and there were 59 doctorates altogether and 1,025 total males in this total group of 2506. All right, so the question statement here said, if a degree recipient is chosen at random, what is the probability that the recipient is male given that they have a professional degree? So what we did in class when we talked about this, we see the word given in professional degree. So we circled professional degree, and that was our family. That's the only group we were interested in. And this is how we wrote it in math symbology, probability of male given professional degree. So we took the total for the professional degrees and put it in the denominator, and then within the family, within that circle, we went looking for the males. Within that circle, the number of males was 45, and we got a 46% probability. So this is how we dealt with conditional probability in the discrete world. Let's see how that could transfer over to the system that we're using now. So for continuous random variables, we go back to the curve we had before, and all we're interested in, the family is greater than 86.932. So the red area is everything that I'm interested in. And then within that area, I'm looking at this green area of greater than 90. So we can think of this being the family, and within that family area, how big is the area of what it is that we're interested in? Which is another way we could go directly to this step. So this is the family, this is the total area that we're considering, and this is the specific area that we're interested in. So if we think about what we saw in discrete conditional probability, we could apply that and go directly to this step in continuous conditional probability and still get to the same answer. All right, hope that made that a lot more clear. Thanks for tuning in.